I'm Paul Plotas. Actually, I graduated in the middle of Danny Manning's career at KU. So, know your audience right there, right?
Mm-hmm. That's cool.
Yes. So I am the department manager of traffic here at Burns McDonnell. Been working here for about 3 years or so now. And we do all things traffic, from signal, pavement marking, signing, temporary traffic control design, to VISN modeling, and planning and projects on that side. Let's see. And actually, since you mentioned working at, is it Adam? I think. Mentioned working at HNTB. We work with all the other consultants in town as well. So we work with Kip Strauss and Joe Blasi. I don't know if that's who you're going to be working with, but you'll certainly meet those guys over there. And we work with those folks all the time as well. So we've got 2 projects, and I think that you guys also are. So Allison will introduce herself when she presents, and then Josh will talk a little bit about himself. Allison will be talking about the Route 44 project in Missouri. It's a design build project. So what that means is that typically projects are design, bid, build, where a consultant will be hired by the city to design the project. A city will then bid the project. Typically will bid the project with the help of the consultant as well. And then they will, based on the bids, hire a contractor to build the project. That's design, bid, build. That's the typical process. Probably about 10 years ago or so, design build process became more popular. And in that process, the city or the DOT will hire a team of consultant and contractors. So the design and build of the project happens at the same time in design build projects. And on the DOT or the client side of things, they'll hire a consultant to help them on the administrative side of the project. And so on the Route 44 project, we were assisting the city. So we were basically, our role was the same as the MoDOT's, Missouri Department of Transportation. And in that project, we did a crash study. So Allison, I'll turn it over to you.
All right, thanks, Paul. So I'm Allison Karagiogas. I graduated high school in Omaha, went to Iowa State and got my undergrad in civil engineering. From there, I worked at MoDOT for 2 years, then another consultant, and then joined Burns & Mac in 2018. So I'm a traffic engineer. I primarily work on signals, striping, MOT. I do some modeling, and then safety is the other area that I'm primarily in.
And
then, yep.
I'm Josh Hartman. Also grew up in Omaha, went to Iowa State. I joined Burns & Mac in 2017 after graduation, and I interned the summer before. Primarily, I do a lot of our traffic modeling, simulation, signal design, lighting design, and traffic studies for Burns & McDonnell. So this is some Burns & Mac related stuff. Did you want to go over this, Paul?
You can, yeah, just a little bit of advertising for Burns & Mac. I'll do this in a minute. We've got 7,000 employees, about 3,000 or so here in Kansas City. Go to the next slide. Here are all of our offices across the country, and then we are also international. And just showing some of the global practices and different parts of projects that we work on, from telecommunications to gas, really just about any type of infrastructure project you can think of, we work on, and oftentimes all the practices will overlap on and work on a single project together. So yeah, this just shows the rankings that we are. We've got a huge power and transmission organization. And as we were talking about before, some of these folks have been hit harder with COVID, and other folks, well, hit harder, and some in a negative way, some in a very positive way from our perspective. All right, so Allison, if you want to take over the 44.
Let's see if we can.
Looks like there's a remote control you can hit up at the top.
Hold on. Okay. Oops. All right. Trying to figure out how much of a lag I've got. All right. So like Paul said, I'm going to talk to you guys about the I-44 design build project, where we operated as the owner's representative for MoDOT. So this, quick recap basically has us help them prepare and identify selection criteria for the overall project. So the original project was slated to be a rehab of 12 bridges spanning over 52 miles. So partway through getting all the documents ready for this project, MoDOT was like, hey, we would like to add some safety components. So they asked us to go through and evaluate the data and figure out what they could add into this project to enhance the safety along the corridor. So we did this using a couple tools, iSATI, which you guys may or may not be familiar with. It's the interchange safety analysis tool that is widely available and is pretty fun to use if you like data. It's data intensive. And so that was used at spot locations. And then we used MoDOT's crash database, which houses all of the crashes within the state of Missouri in it. And this allowed us to do some large overarching analysis. So before I begin, for anyone who's not familiar with crash terminology, CABCO is the severity rating scale for crashes. So K is fatals, A are severe injuries, B minor injury, C potential injury, and O is property damage only. So we look at different combinations of these when we're doing analysis. For the first pass of analysis, we just analyzed eastbound and westbound I-44. And we looked at all severities, and we were just looking at a very basic number of crashes per mile. The green line, the red line, whoops, that's red. The red line is the average of all the crashes on the corridor. And then we've got the standard deviations with the green and the blue. So the blue, or purple or blue, is the second standard deviation. So we were just trying to see what's going to be, fairly statistically significant. There we go. So this was the same analysis, but we took out the PDO crashes to see if there was any areas where we were seeing a large number of injury and above crashes. Oh my God. Let's see. Okay. Sorry, I'm having controls issues. So the third paths of our analysis included looking at all severity crash rate per mile, the crash rates and then the crash rates for just the injury and above. So for this corridor, we were finding that we were seeing about 10.5 per 100 million vehicle miles traveled. We compared this to the statewide average, which is 23.4. So, we weren't seeing as high of crash rates on this facility as other areas in the state. And similarly, we were seeing for just the injury and above, about 57.17 crashes. Oh. So yeah, so for the quarter, sorry, I'm just having a hard time talking today. The quarter average, okay, and so backing up, so we had the 10.5 per 100 million. We did have 3 miles within the project that were 2 or more standard deviations greater than that average. And so that was kind of an important point to look at. Okay. So we identified key points within the corridor that had statistically significant number of crashes that we wanted to look at in more depth. So you can see those locations. So the first was the I-44, I-49 interchange. This location was found to have a crash rate above the corridor average, and most of these crashes occurred in the loop ramp weave areas, and as well as the acceleration and deceleration lanes. Because the mitigation measures would not be practical at this location due to the project scope, the location was not recommended to be included for the design build teams to look at. Then we have the interchange near Prigmore. This interchange was actually recently built when we were looking at the data, so we did not have enough after data to evaluate whether this would be a good to be able to identify what we should be looking at from a safety perspective, and so it was also not included as something the design builders should look to include. The Route O, Z, and 96 interchange was actually identified at the very beginning of the project as an area of interest. There are a total of 69 crashes within this segment, and 38 of those were identified as out of control crashes. And so MoDOT had the idea that, this would be a good area to focus on to see if there were any improvements we could make with this project. So this is kind of showing how their database works. They have within it, it'll put densities for the crashes. And so you can see this is looking at just the out of control crashes that we saw and where those were occurring. So entrance and exit of curves, and then at the different ramp terminals. These tables show the predicted crashes versus what the existing crashes versus what we were seeing with the existing crashes. From these tables, we can see that there's a higher than predicted number of crashes occurring along I-44. The key areas where this was occurring was near the horizontal curves and the eastbound on-ramps, which you guys kind of saw before with the heat map. In addition to this base condition where we just looked at what was out there today, we evaluated an alternative where we were eliminating 2 weave areas, and we changed the grade separation of I-44 and Missouri 96, which would allow us to reconfigure the ramp locations. And so the results of that are shown here. So this basically results in a reduction of 9 crashes in 10 years. that doesn't seem like much to you and me, but when you're looking at being able to save lives, reducing the number of crashes, any reduction in crashes is very important to look at. And so 9 crashes, 10 years, not even a crash per year, it really doesn't seem like much, but it will add up over time. So we have these quantitative benefits, and we also believe that the elimination of the westbound off ramp, which was a loop ramp, which had an advisory speed of 20 miles per hour, would help eliminate the speed differential and reduce the number of rear ends. So we also expect to see an increase or a decrease in the number of rear ends that aren't fully reflected in this analysis. So the fourth area of interest that we were looking into was at Mount Vernon. This area was also included for further analysis, as well as an area of interest for the design builders to incorporate. The primary crashes that we saw in this area were due to speed differential. There's a very high number of heavy trucks in this area, and so many of the crashes involved those heavy trucks and the short acceleration and deceleration lanes that were out there. So when we ran the models, it looked when we ran the models, we were seeing about a reduction at 1 crash every 10 years. But when we were looked at it from a different perspective, using CMFs and maybe using CMFs, we saw that there would be about a 22% reduction in crashes in the area. So this was a big deal because do it those. So at those locations, we looked at what the existing crashes were, and we saw, wherever there was smaller shoulders, there were an increase in traffic, in crashes. So we were able to use that to say, hey, if we tell the design builders to, add some widening, that should increase the safety at these areas. So the inclusion in the bid. So we ended up putting together these different rankings to be able to be included in the bid. However, the only things that were included in the winning bid and all the other subsequent bidders were signing and pavement markings. These are fairly low-hanging fruit that the DOT tends to do themselves, but this allowed us to do some lessons learned, basically that we needed to award either more points or more money for those safety aspects to be included, as well as just to see, as well as starting out the project as knowing we want to include safety and making
Thanks, Allison. So here, let me see if I can get my laser pointer up. There we go. So for this presentation, we're going to be talking about one of the bigger projects that we have going on at Burns McDonnell. So I'm sure many of you have heard about the LaGuardia Airport in Queens, New York. This project is located just north of Queens, kind of close to Rikers Island in New York City. As you can see on the right, over here is the airport. And from here you can see there's 4 terminals, Terminal A, B, C, and D. Burns McDonnell is doing half of the airport, Terminal C and D, which are the Delta terminals. And then Terminal A and B is being redone from a different consulting company. So with this, it is a $8 billion project. Our portion is $4 billion. And when you zoom into here, you can kind of see how busy LaGuardia Airport is. You can see all these planes being backed up, and this is just a Google Earth image taken at a certain time. Planes taking off and landing at the same time on 2 different runways. It is very busy and has a lot of traffic going throughout it. So this rebuild was definitely needed for this location. There we go. So here's a project overview of the terminals that we are working on. So C and D, this is the existing, you got Grand Central Parkway, the interstate system right here with some button hook entrances and exit points. It is very congested, has parking lots in the middle, a taxi stack right here, and then a parking garage. So over here in the new terminal design, we're consolidating C and D into one large Terminal C head house. And we're also getting rid of a lot of these sharp button hooks where you go from 60 miles an hour down to 20 for safety. So we have a bunch of new flyovers that fly over and bring you over into a more free flow, less stopping, a safer design with a lot more capacity. Here's a blow up, just to kind of give you an idea. So there are 2 levels in the existing design, a departures at the top and arrivals at the bottom. As you can see, you're going up and down quite often instead of just staying on a departures level in the current existing design. So here's some proposed renderings of the new LaGuardia Airport. Definitely shows a sleeker design, bigger, should be able to impact way more airplanes. One thing I did not mention is that Burns and McDonnell, we have a different practice here that does the aviation side, which is from the curb, from the terminals to the airplanes to the actual fueling and the runways, and they are working on that portion of the new design. And then our transportation group is working from the curb in. So curb side, land side, and then air side is the other difference. And what we are doing is more the roadways, the cars getting there, people getting to the airport, and then our aviation group is taking care of them as soon as they enter the actual airport for the new design. Some new renderings for different roadways that our architecture group came up with to kind of give an idea for Delta to kind of more visualize what they're seeing. Some interior of what the new airport's going to look like for different gates. As you can see, they're sparing no expense for this new airport. So when it comes to airport traffic design and roadway design, you have pretty much 4 main things that you need to utilize. 2 of them are standards, and then we use 2 software packages predominantly. So the ACRP Report 40 pretty much gives you the entire lowdown of airport design, the different roadways, different speeds that you need, the different modes of the transportation that utilize airports, and how to use occupancy factors and figure out how to translate planes full of people into passengers and cars, getting to the airport and leaving. Then your classic highway capacity manual just for capacity of roadways. And then the main software that we use is PTV VSIM. This is the Cadillac of microsimulation. We can input all this data. It gives us results. We can analyze different construction stages, the final build conditions. We can get levels of service, delay, parking, pretty much anything that we need to analyze different construction stages and final design ideas. We can vet through VSIM before just testing it out on the public. And then Synchro 10 is the software that we are using to analyze the different signals that we might have to use during construction and final, just to get different levels of service, excuse me, and then evaluating pedestrians crossing these different signals. So with LaGuardia Airport, it is the only major airport in the New York City area that is not connected by a subway line. So predominantly, the only public mode of transportation is the bus. So without having the subway line, pretty much everyone has to drive there with different modes of vehicle. We first started this project back in 2014, Uber and Lyft were not a thing. So throughout the project, we had to incorporate more for-hire vehicles such as Uber and Lyft, whereas before it was more yellow cab taxis in New York City that you're predominantly used to knowing about. And that's where the chunk of traffic mostly cut into, and private vehicles. The other vehicles that we looked at were your classic shuttles from parking lots and or hotels, and then limousines are also pretty predominant at the LaGuardia Airport. Now, when we evaluated all of these things, we actually sent people out to kind of get evaluations for the peak hour of most cars at the airport, and we wanted to see what's the average occupancy in these things. You find most passenger cars average about 1.7 people. Most Uber is about 1.2. Buses, you get about 12 to 13. So you go through all of that, and you also want to see how long they are staying at the curb. And with the staying at the curb, passenger cars, your mom's dropping you off, you want to say goodbye, kiss goodbye, whatever, but you don't do that with your Uber driver, so you leave a lot faster. So we have to evaluate those metrics as well while putting it into the actual model to evaluate. So typically you would think, oh, just get traffic counts at the curb and that's how you figure out what your traffic is. Yes and no. So for airports, for planning for the future, when this thing is actually going to be built in 2026, we have to look at what the flight data looks like. How many planes are taking off? How full are these planes? What time are they going off? So we have to look at that kind of data. And from here, you can kind of see this is the hours before and after a plane going at one gate. So before, the plane's taken off right at this line. So predominantly you have 2 hours before, 3 hours before. So at 2 hours before, you're looking at about 50% of people are at the airport already. So they've arrived within the 4 hours to 2 hours mark. And then once the plane's taken off, you have 100% of the people on the plane are there. So it's a statistical evaluation that we need to evaluate for finding when the peak time is. And then the same can be said once passengers leave the airplane. Some people are booking it at 10 minutes. As soon as it lands, they're at the curb. Otherwise, most people take about an hour to get their bags, walk through the terminal to get to the curb and actually use the mode of transportation that they're going to be utilizing. And all of that is layered on several gates, so it takes a lot of analysis to try to get a final number for what's at the curb for a certain peak hour. And why we do all of this is we want to evaluate how the level of service and what you can expect going to the airport. So for the Port Authority of New York City and New Jersey, which is the agency that we evaluate to and what standards we need to keep to for this airport, they allow for a level service C or D. As soon as you start getting to level service E, that's no good. You don't want cars backed up to the interstate and having pilots walk across the tarmac to try to get to their plane. Predominantly for the new design, we're looking at level service B and A. So Delta wanted to make sure that the performance of the airport, they wanted to make sure passengers were content and happy getting to the road, not already upset with traffic, was their entire goal. So they upped the capacity, they spent more to have more capacity to allow that for their customers. So right here we have a actual kind of simulation of the airport that we put into the VISM model, and we'll have it run right here. So this is kind of a construction phase that we're going through and vetting some certain ideas. And in this, you can kind of see how the different colors mean the different modes of transportation. So the black cars that you see kind of going around are your Ubers, your Lyfts, your for-hire vehicles. The red cars are your passenger cars, your personal vehicle. Yellow are your yellow taxis. And then some of your bigger vehicles over here, the greens and the browns, are your buses, your courtesy shuttles. And in the actual simulation, when you see that they park and turn white, that's them actually parking at the curb and then dwelling or staying there for the amount of time that we kind of discovered for that kind of mode of transportation. So here's the zoomed in area. So you can put in traffic timings, signal timings right here. So black, and then it goes to, or red to a green cycle. And with this, we can kind of evaluate different construction phasing. Sometimes it's not the roadway geometry. A simple signal change can help make the traffic move more smoothly, and we don't have to try to find more room for roadways or anything like that. So this software allows us to save money and time for construction as it's going on, which is why we do this and why Delta is willing to pay for this modeling experience. We'll let that finish running for a little bit. So this is our permanent end state model right here. So the orange that you're going to be seeing is the third elevated roadway. So this is probably 50 feet in the air going around. So coming off the interstate, you can kind of envision cars coming in and then looping around to get to the airport, so they can keep up speed and not be backing up the interstate. The blue roadways are your elevated departures level, so that's probably 20 feet in the air. And then the gray, which we do have shown right now, would be the arrivals level, which is directly underneath the blue. And we'll let this run. So you can see from here that a lot of the vehicles are going around. It's way more free flow. We took out a bunch of signals. The existing LaGuardia airport had probably 7 or 8 signals. We took all those out except for 2. So there's 2 signals in the final condition, which should ease traffic to be more free flow, improve the passenger experience is the main goal for this design. And just plenty of lanes for any large rush. Usually the Christmas season or the Thanksgiving season holidays, you see a huge influx of traffic at the airport. And with this, the client really enjoys seeing the power of this software, because we can go into a 3D and it gives a more real feel of what this is going to look like. So this is great for presentations, and it helps with the higher ups at Delta and our different clients to kind of get a bigger idea of, okay, we're going to be building this in the next 5 years. I want to know what this is going to look like. How is it going to perform? And from the 3D effects, you can really show what they're building, what they're spending all this money on, and it helps kind of show what all the software can do and what they want to show their shareholders as well. And then this gives a secondary angle, and you can kind of see the yellow or the orange roadways are above the blue, and then you have the arrivals down below those. So it kind of gives you a different angle, because the bird's eye, you can't really see the elevation differences. I'll let this video run out so you guys can kind of see how it all kind of works. And right in here is a garage with vehicles exiting through a toll gate to pay their parking ticket for however long they were there. And with that was the end of our presentation.